Hello everybody. In this video lecture, we will learn Hopkinson's test. This is Sonakshi Riker. This video lecture is divided into 3 parts. In the first part of the video lecture, we will learn the purpose of this experiment, the apparatus required, theory behind the experiment. The theory will include the principle behind the Hopkinson's test, what is the basic method they have used in the test. Also, we will learn the connection diagram of this experiment, and later in the second part of the video lecture we will demonstrate the circuit connection and the conduction of Hopkinson's test. In the third part of the video lecture, we will study the tabulated data. We will see how we will calculate the different parameters required, and we will see at the later part the result and inference of this experiment. So coming to the purpose here, we have different types of indirect method of testing DC machine, and Hopkinson's method is one such indirect method. So the purpose of this experiment or this Hopkinson's test is to determine the no load constant losses, or I can say to determine the constant losses of the DC machine or DC motor, and using this we can calculate the efficiency of the motor for different loading conditions. So the actual goal or the objective of conducting the Hopkinson's test is to determine the constant loss. Now this constant losses will include iron losses and the friction and windage losses and a small part of stray loss. So these will be together, we'll call it as constant losses, or we can also call it as stray loss. So this will be determined in this experiment. There are different names for Hopkinson's test. One of the way we call it is regenerative method or back-to-back test. So the Hopkinson's test is a very useful method when it comes to calculating the efficiency of the DC machine. So the aim of the experiment is to run to mechanically electrically coupled identical DC shunt machines back to back and determine their efficiencies. So these are the apparatus required. So this is the circuit connection. It is a full load test and it requires two identical machines which are coupled to each other both electrically as well as mechanically. So out of these two machines, one machine is operated as DC motor and the second machine is operated as DC generator. So here one machine acts as a load on the second machine. So that is the reason why we call it as back-to-back test. And also you can see that the power output of one machine will act as a power input to the second machine. You can see that the mechanical power output of DC motor is actually mechanical power input to the DC generator. Similarly, the electrical power output of DC generator is electrical power output to DC motor. So here the energy is not wasted, but it is used within the experiment. So we call it as regenerative test. When both the machines are operating at full load, the supply input is equal to the total losses of the machine. That is, when both are operating at the full load, the mechanical power output will be utilized by the DC generator and the electrical output will be utilized by the DC motor. So in this case, whatever the power we take from the supply will only be the constant losses. Whatever the constant losses that will occur in these two machines, that constant losses will be supplied by this DC supply. That is the reason why the power input to this experiment is very small. When a machine is started or when this motor is started using a variable rheostat RSHM, we adjust its speed to its rated value. The first thing that we do here is, both using starting rheostat as well as RSHM, we bring the speed of the DC motor to its rated value. Then we change the field rheostat of DC generator, that is RSHG, and we vary the terminal voltage of this DC generator. So we will vary till this terminal voltage is equal to the DC supply, that is 220 volt. So once the DC generator is, the terminal voltage of the DC generator is equal to its DC supply voltage, then we say that the generator will be in floating condition. That is, it neither takes power from the supply nor supplies power to the DC supply. So under this situation, how do we verify this condition, that is floating condition of the generator? And that is done through using this VS, that is 0 to 600 volt voltmeter. So this will actually show us that as we keep on increasing the RSHG, the voltmeter will read from, it will start to decrease, which means that the voltage difference between this point and this point starts to decrease, which means the terminal voltage of the generator is actually increasing. And once it reaches this 220 volt, this voltmeter will show you 0. Okay, now if in case as we keep on increasing as we keep on varying RSHG, if the voltmeter here, if the voltage reading starts to increase, it means that the polarity that we have connected is the wrong polarity, and we have to interchange the armature, we have to interchange the terminals of the generator. So that we have to keep in mind. Clear? Now once we are changing RSHG, that is we are bringing it from cut in to cut out position, and the voltmeter is decreasing, and this voltmeter value is decreasing, and we get this voltage equal to the supply voltage, then it's in the cutoff floating condition, and we close the SW switch. Once we have ensured that generator is in floating condition, we close this switch. So now what happens here is, now as you keep on increasing the field voltage, the field rheostats, both motor and generator field rheostats are varied to attain different loading condition, and we take the readings. Now what exactly we are doing here is, as we keep on increasing the field current of generator, the flux in the generator increases, and the induced voltage of generator is increasing. Now once this induced voltage of generator is increasing, this means that this induced EMF in generator will be greater than induced EMF in the motor, due to which the current through the armature increases. Now in order to current in the since the current to the armature of the motor increases, the current from the armature of the generator will also increase. So we can say that load on both the machines are actually increasing. The load on both the machine is increasing. And also in every step, whenever we are adjusting both the field rheostat, we have to keep in mind that the speed remains constant. We have to change the armature voltage of the generator, and we will be changing the armature voltage of the motor. We'll be increasing it in step, and in each step we have to make sure that the speed of the entire system remains constant at 1500 rpm. So the speed will remain constant. We will be changing the rheostat, both the motor field rheostat and generator field rheostat, and we will vary the armature voltage of the DC generator in step, and we will take down all the meter readings. So in the next part, this is the nameplate details. So we are required two identical DC shunt machines. So but we cannot actually get identical machine. So those DC shunt motors which are nearly identical, we have chosen those two DC shunt machines. So this is the procedure of this experiment. In the next part of the video, we will learn, or we will demonstrate the conduction of this experiment along with its circuit connection. So we'll see the conduction as well as the circuit connection.
So now we will conduct the experiment on Hopkinson test. Basically, Hopkinson test is used to determine the efficiency of the two identical machines. So this experiment requires two identical machines, and it is mechanically coupled. Okay. So first I will explain the connection of the Hopkinson test requirement. Okay, as per the circuit diagram, you have to connect the motor circuit. You have a motor, armature terminal and the field terminal. So you have the rheostat connection for the field terminals and the starting rheostat for the armature terminal. So the starting rheostat should be in cutting, and armature, the field rheostat of the DC motor should be cut out. Okay, for all the paths, for the field path and armature path, you have a meters connection to measure the current in that. So that apart from this beside the motor circuit, you have a generator circuit. So generator circuit having a field rheostat here, and this is in cutting position, and the armature terminals having the current, the meters are connected here to measure the armature current and armature voltage also. And here one more interesting thing is that there is a switch is there in between the two motor circuit and the generator circuit. This switch should be initially switch off, and it will switch on only when the voltage across the two circuits should be 0. So that is ensured by this meter. Basically this meter should reach 0 when you want to switch on the two circuits through the switch switch A here. Okay, so now we will start the experiment basically, and for that you have to switch on the DC supply. When you put on the DC supply, you will see that there is a voltage measured, the voltage across the DC supply you can measure, and the current flowing through the armature also you can see from the A3 meter. And initially the speed is 1289. I have to bring it to the rated speed by wearing the starting rheostat. Cut out the starting rheostat slowly so that the speed is increases. You can see this variation of the speed by cutting out the starting rheostat. Okay. Yes, it is 1500 rpm as per the specification. So it will be 1500 rpm. Okay. Then after bringing to the rated speed, so because of the motor coupled to the generator, the motor is running at a rated speed. Then voltage is developed across the armature, the generator side. So the generator is built up in the generator because of mechanically coupled. And then you have to observe that there is a reading on this meter. It is not showing 0. So your switch should be off. You should not switch on when the voltage is there. This you make it 0 by wearing the DC field excitation. So you have to make a cutout. Initially cut it, and it will make you can see this voltmeter reading. It is coming to 0. Yes. Still more. Okay. Now it is 0 exactly. Now you have to stop wearing the field rheostat of a generator. Then you have to see that the speed is decreasing. Okay. And you have to make the starting rheostat to bring the rated speed by cutting out. Okay. So then you have to solve it. Now it is correct. It is exactly it is coming very close to this. Now you switch on the supply. Now you switch on the switch between the two circuits. Now after switching, there is an increase in the speed is there here. Okay, you can observe that. You make it the rated speed. Now your generator is in the floating condition after closing the switch. It means it neither take out current nor the injecting the voltage to this one. So now at this condition we will call it as a floating condition. Now I will make the generator deliver some power through excitation of a DC field shunt rheostat. So now I will make the generator to deliver some power, that is only through excitation of a DC field generator. So now you vary that at each step. At each step I have to note down the armature current. Armature current is not still developing because it is not you have to vary. So now you have to increase the excitation by cutting out the field. So then the speed is decreases. You have to maintain the speed by cutting out the. This is a tuning between the starting rheostat and the field rheostat of a generator to keep this speed is 1500. At each step of the reading, you have to note down this constant speed. So now we are making an exercise to bring it to the rated speed by varying the excitation. Yes, little bit. Okay. Now the current starts. Now is current. It starts. Okay. So at each step of the current, yes. Now the speed is close to this. Now note down the current. It started, and at each step the speed should be exactly the rated speed. And in terms of current steps, it is 10 amps rated. So 2, 4, 6, 8 in steps of each steps. That is in steps of current. You have to note down the armature voltage and the current you have to note down, so that you are calculating the power delivered from the generator to this. This is the, after noting out all the readings you have to note down at each step of the current of a DC armature generator. So that is each step you have to note down all the meters. Okay.
In the last part of this video, we have demonstrated the connection of this experiment, the circuit connection of the experiment. We have also demonstrated the conduction. So in this part, we will study I'll explain the readings tabulated, and from the readings, we will also see how we will calculate the no load constant losses. And based on the calculation of no load constant losses, we can calculate the efficiency of the motor for different loading conditions. So first thing is, this is the data we have tabulated. The first and foremost thing I've told you in the first part itself, that in each reading we will keep the speed of the motor constant. So we have kept it constant around 1500. A small variation in the speed will be there. We cannot avoid that. Now coming to this, you can see there are 5 ammeter readings. So this is your field current of DC motor. This is the armature current of DC motor. This is the field current of DC generator, and this is the armature current of the DC generator. So as we adjust the field rheostats of both the machine, we are actually increasing the armature current of both DC motor as well as DC generator in step. So we are keeping armature voltage of DC generator as a reference, and we are varying the armature current of DC generator in steps, and we are obtaining different readings. Clear? So now here you can see that by adjusting both field current of motor as well as generator, you're increasing armature current in steps, as well as simultaneously we have to keep the speed constant. But this part we have already seen in the conduction. Coming to the calculations. So the calculations here will have 3 parts. The first part is determination of stray losses, or I can call it to be more specific, it is no load rotational losses. Next we have efficiency of machine working as motor. Now there are 2 machines, so we are calculating the efficiency of 2 different machines. So this is the efficiency of the machine which is working as motor, and this is the efficiency of the machine which is working as generator. Don't get confused with the Swinburne's test. In the Swinburne's test, we conducted experiment only on one machine, and we calculated the efficiency when the same machine was acting as motor and the same machine was if it acts as a generator, what will be the efficiency that was predetermined in the Swinburne's test. But in case of Hopkinson's test, we are not predetermining the efficiency here. The machine which is acting as motor, the efficiency is calculated using its losses, and machines which is acting as a generator, its efficiency will be calculated. So you cannot correlate or you cannot compare the result you have obtained in Swinburne's test and the Hopkinson's test. So that result cannot be compared here. Okay, that keep that in mind. So first thing is determination of no load rotational loss. So first thing is the power drawn from the supply. Now that power drawn will be nothing but whatever power drawn from these two terminals, the positive and negative terminal. So that is nothing but the voltage across this terminal and current to the supply. Now the current to the supply is given by I2, that is this current. So whatever this current, now this power input will exclude the field power or the field copper loss. Now whatever this V1 I2 we are taking, it is only for motoring action. Whatever power we have taken from the supply for motoring action, this will exclude the field copper loss. So that is the reason why we are taking I2 current. And what is the voltage here across these two terminals? Since this rheostat will be completely brought to cutout position, and we close the SPST switch during the conduction, this becomes a short circuit. So whatever voltage we get across this, that is the V voltage, V into I2. This total voltage will be the power taken from the supply for the motoring action. This will exclude the field copper loss. Field copper loss will not be included. Okay, so that is the power input. And total armature circuit copper loss will be equal to armature current into, square of the armature current into armature resistance plus square of the armature current into armature resistance. And this will include, we are taking both motor as well as the generator. So this is the circuit copper loss. So the no load rotational losses or the stray losses will be equal to the total power input minus the armature circuit copper loss. So here it has to be V1 I2 minus I3 square RAM minus I5 square RAG. Either you put a bracket here. When you put a bracket, this becomes plus, but since the bracket has been excluded, this has to be minus. To make that correction, it is V1 I2 minus I3 square RAM minus I5 square RAG. Clear? So this will give us the no load rotational losses. Now here we will assume that both the machines will have equal no load rotational loss. So for per machine we can calculate the no load rotational loss using this. We will just divide it by 2. Now to calculate the efficiency of the machine working as motor. So for when we are calculating efficiency of the motor, we take input minus losses divided by output. Okay, so input to the motor is V1 into I1 plus I3. I1 plus I3, I1 is the field current and I3 is the armature current. So here it is including both field input as well as the armature circuit input. So this is V1 I1 plus I3 minus the losses. These are the losses. This is the copper loss, this is the field loss, and this is the stray loss. These two are the field and armature circuit copper loss. So that the losses will be subtracted from the input and we get output of the motor, and using this expression we will calculate the efficiency using the last expression. Okay, so next one, this is the efficiency of the machine working as generator. Now here again the output of generator will be taken because we cannot calculate the input of the generator because it is a mechanical input. So we go for output of the generator. So it is V1 into I5. I5 is nothing but the armature current of the generator. So V1 into I5 minus divided by the output plus losses. These are the losses. This is the armature circuit copper loss. This is the field circuit copper loss. This has to be V1. This is not I1. This is V1 into R4 or RA. Sorry, this has to be actually V1 into I4. Make a correction here. Sorry, I cannot make a correction in this tab. But to make a correction, this has to be V1 into I4 plus WS. Clear? Sorry. Plus WS is the stray loss per machine. So using this, we'll calculate the losses. And this is the typical graph, efficiency versus output graph for both motor as well as the generator. Okay. So now these are the sample calculation. For the first calculation, we have calculated the stray loss or no load rotational loss of each machine. So this is the power input for motoring action, which is V1 into I2. Only for motoring action, what is the power input? So for that we take exclude the field copper loss or field current input. So we get V1 into I2. That is being supplied from the DC supply. Now here motor is getting supply from two sources. One is the DC generator, that is this current, and second one is the DC supply. The armature will get DC supply from this path. So that is the reason why we take V1 into I2. So V1 into I2 minus this armature circuit copper loss. So we get around 598.8 watts. For each machine we'll get around 279 watts. So now we'll calculate the efficiency of the motor. This is the power input and this is the total losses divided by the power input. We get efficiency around 63.21%. Similarly, we'll calculate for generator. This is the power output of a generator, and when we calculate the losses, we get efficiency around 48.11%. So here we can see that we can calculate the efficiency. We have tabulated the results here. For each result, we will be calculating the no load rotational loss, and from there we will calculate the efficiency of the motor. So as we change the load, we get the efficiency. Clear? Now for power output here, for the power output we consider this value for the generator, and we will consider this value for the motor. You can see this expression, output of the motor. So whatever value you get here, that will be your x-axis for motor, and this value will be your x-axis for your generator, and similarly y-axis will be your efficiency. So this is how the calculation has been done. Now coming to the advantages of this method, now coming to Swinburne's test, it is applicable only for small machines. When we go for larger machine, we cannot go for Swinburne's test. So that is the reason why we go for Hopkinson's test. The Hopkinson's test will be more suitable or apt for or you can say more appropriate option for large machine, because when it as you keep on increasing the size of the machine, under no load condition you cannot make it run for 5 or 10 minutes as we have done in Swinburne's test. So that can be avoided in Hopkinson's test. And also whatever the power input you take from the supply is only the losses in that machine, so the power input is very less, so Hopkinson's test will be much suitable. And also since both the machines are operating at full load condition, in Hopkinson's test the effect of full load armature reaction and full load temperature rise will be considered, whereas in case of Swinburne's test we are making it run under no load condition, so the full load armature reaction and full load heat temperature rise has to be avoided there. That effect cannot be determined in Swinburne's test. But here, since both the machines are operating under full load condition, both the armature reaction as well as the heat temperature rise under full load condition can be included in the analysis. Okay, that is the reason why whatever the stray losses we get or the no load rotational losses we get will be much more accurate than what we get under Swinburne's test or any other test. Okay, now coming to the disadvantage of this method, is one of the biggest disadvantage here is the requirement of identical DC machine. You cannot get two identical DC shunt machine. Even in the experiment we've seen, we are not using exactly identical machine, because we can't, the availability of exactly identical machine is very less. So we have used nearly identical DC machine. So that is one of the limitation of this test. Okay, to conclude, in the conclusion part, we have obtained first I'll explain the result part. We have obtained the efficiency versus output characteristics of both machine working as a generator and the machine working as a motor. And first thing that we have done here is we have successfully demonstrated the Hopkinson's test, and from the results or from the data tabulated, we have determined the no load rotational loss of the machine, which includes the friction, windage, iron loss and the stray loss. And from the no load rotational loss, we have calculated the efficiency of the motor for different loading conditions. And we have also plotted the efficiency versus output graph for both the machine. In this experiment setup, we can see that the efficiency of the motor is much greater than efficiency of the generator. This is only because of the fact that the armature as well as the field copper loss in generator is greater than the field and armature copper loss in the motor. This is all based on the design of this machine. The machines are designed so in such a way that the generator copper loss is much greater than the armature copper loss. Now that is the reason why we get efficiency of the motor greater than efficiency of the generator. We cannot generalize the statement. As you keep on changing the machine with different design parameters, this particular statement will change. But from a single test, we can calculate the no load rotational loss, and from there we can calculate the efficiency of the machines for different loading conditions. So this method, from using this method, we can calculate the efficiency of the motor. This becomes one of the most useful method of testing the DC machine. Thank you.